Hi, my name is Mr. Peck from Ideas Inc. School, and today we will discuss about sound. Sound energy is transferred through a medium due to collisions between vibrating particles. That is why sound energy can only be transferred through a solid, liquid or gaseous medium, and it is not possible to transfer sound energy through a vacuum. For example, outer space is a vacuum that is void of particles. Thus, when an explosion happens in space, no sound can be heard. Next, we will discuss how sound behaves as a wave. Sound energy travels through a medium as a longitudinal wave. This is when the particles vibrate in a direction that is parallel to the wave's propagation. As sound moves through a medium, the particles will form regions of compressions and refractions. Regions of compressions is an area where particles are more densely packed. Thus, pressure in this area is greater. Regions of refractions, on the other hand, is an area where particles are more spaced apart. Thus, pressure in this zone is lower. A better way to visualize this phenomenon is with a slinky spring toy. When the spring is placed horizontally on a flat surface and pushed back and forth, you will notice that the spring is moving in the direction of the applied force, and the coils are moving back and forth, which is parallel to the motion of the spring. And if you look closely, there will be regions of the spring which are compressed and parts of the spring which are more spaced apart. And how sound travels is very different to that of light. Light energy travels as a transverse wave. In a transverse wave, particles vibrate in a direction that is perpendicular to the wave's propagation. A good visualization of this phenomenon is performing rope exercises at the gym. When a rope is swung to create a wave, this wave moves parallel to the floor and away from the user. However, when we take a closer look at the motion of the rope appears to be moving up and down instead of back and forth like the spring toy. This is the main difference between a transverse and longitudinal wave, where the particles move perpendicularly instead of parallel to the wave's propagation. In the next part of the chapter, we will be talking about the speed of sound and how we can measure it. The speed of sound is about 300 to 400 meters per second in air. Fun fact, if a plane is traveling at a speed of Mach 1, it is traveling at the speed of sound. If the plane manages to travel at Mach 2, it is traveling at 2 times the speed of sound. And when the plane accelerates from Mach 1 to 2, a sonic boom can be heard. So how do we come up with a simple experiment to measure the speed of sound? All we need is 2 individuals to stand a certain distance apart from each other. One of them will be firing a starter pistol while the other will be holding onto a stopwatch. When the pistol is fired, the person with the stopwatch will start the timer once the flash from the gun is seen. And the timer will be stopped when the sound from the pistol is heard. To calculate the speed of sound, we can simply take the distance between the 2 individuals and divide it by the time measured. However, how can we improve the accuracy of our experiment? We can repeat the experiment a few times and obtain an average speed. This way, we can reduce inaccuracies caused by human errors. We can make sure that the distance between the 2 individuals is large enough for the person timing to detect and react accurately to the flash and sound from the pistol. We can also interchange the position of the 2 individuals to reduce errors caused by environmental factors. Lastly, we can use a microphone and camera to improve our measurements. In the next part of the chapter, we will move on to the concept of echoes. An echo is a result of sound waves reflecting off a surface. When an echo is heard, it is lower in volume as some of the sound energy is absorbed by the surface and some waves are reflected away from the observer. Additionally, an echo possesses the same frequency as the original sound because the number of waves striking and reflecting off the surface remains unchanged. Some applications of echo include estimating the depth of oceans and finding schools of fish. We can also use the concept of echoes to measure the speed of sound. In this experiment, we will first position metal plates a certain distance away from a wall. The 2 metal plates are set up in an electrical circuit such that when the 2 plates come into contact, the circuit is closed and an electronic stopwatch starts. A microphone is then used to detect the echo coming from the wall. Using these measurements, we can find the speed of sound by taking the distance between the plates and wall. Multiply this value by 2 and dividing it by the time taken. In the next part of the chapter, we will be talking about how to describe sound in a scientific manner. We will be using pitch and loudness to describe sounds. Sounds with low pitch have a low frequency, where frequency is the number of complete waves passing through a point per second. As such, sounds with lower pitch will produce waves which are more spaced apart. On the other hand, sounds with high pitch have a high frequency. Thus, high-pitched sounds will produce waves which are more densely packed, meaning that the peaks and troughs of the wave will be positioned closer together. How about quiet and loud sounds? The loudness of a sound is measured using decibels. A quieter sound will produce waves with a lower amplitude. This results in the sound wave having a shorter height and depth. A louder sound, on the other hand, will produce waves with a higher amplitude. Their waves will be taller and deeper as compared to quieter sounds. Next, we will move on to some other facts of sound in our daily lives. The human audible range is from 20 Hz to 20,000 Hz, where Hz is the unit of measurement for frequency. A sound produced over 20,000 Hz is known as ultrasound, while a sound below 20 Hz is known as infrasound, both of which cannot be heard by humans. As we age, we tend to lose sensitivity to sounds at higher frequencies. That is why some children can hear sounds emitted from dog whistles but adults can't. And when your music teacher asks you to play an instrument at 1 octave higher, she meant for you to play at double the original frequency. Some uses of ultrasound include using it to scan for the fetus in pregnant mothers. Ultrasound can be used to clean jewelry and even to reduce the size of kidney stones. With regards to musical instruments, let's explore how different types of instruments can produce a range of sounds. When it comes to wind instruments like flutes and clarinets, a shorter column of air will produce a higher pitch, while a longer column of air will produce a lower pitch. In string instruments like guitars and violins, shortening the string, using a thinner string, or tightening the string will produce sounds with higher pitch. And with percussion instruments like drums, tightening the skin will produce a higher pitch while loosening it will produce a lower pitch. But what if we want to produce louder sounds? All we need is to vary our strength or force applied. We can blow into a flute with a greater force, pluck the strings of a guitar with more strength, or strike the skin of a drum with a larger force in order to increase the volume. Next, we will discuss about environmental factors that can affect the speed of sound. The density of the medium will have an effect on the speed. The greater the density, the faster the speed. That is because, as density increases, the number of particles per unit volume increases, and the frequency of collisions between vibrating particles increases. A good example to demonstrate this concept is to imagine how sound travels through the air after the rain. When the air becomes more humid after the rain, the density increases as there are more water molecules. This will increase the frequency of collisions between particles and thus increasing the speed of sound. Another factor that affects the speed is temperature. As environmental temperature increases, the faster the speed of sound. Higher temperatures causes particles to have higher kinetic energy. This in turn causes particles to vibrate faster and move at higher speeds. Therefore, the frequency of collisions between particles increases. That is why sound travels faster on a hot day as compared to when the weather is cooler. Lastly, please note that air pressure has no effect on the speed of sound. In the next part of the chapter, we will be discussing about the formulas involved in calculating the velocity of sound. The formula is V equal F times lambda, where V represents velocity in meters per second. F represents the frequency of sound in hertz, and lambda stands for the wavelength of the wave measured in meters. Please note that the wavelength is measured between two corresponding points of two consecutive waves. For example, the distance between two consecutive peaks or two consecutive troughs is a wavelength. Furthermore, frequency can be calculated using the formula F equals to 1 divided by t, where t represents the period of a wave. This is the time taken for a complete wave to pass through a given point. In the last part of the chapter, we will be talking about how sound reaches our ears and how the structure of the ear helps us hear. Sound energy from a source reaches our ears due to collisions between vibrating particles. The sound wave is captured by the pinna of our outer ear and channeled through the ear canal towards the eardrum. The eardrum vibrates to the frequency of the sound, and in turn causes the bones from the middle ear to vibrate as well. The bones in the middle ear are namely the malleus, incus and stapes. These bones help to amplify the sound and send vibrations to the inner ear. In this part of the ear lies the cochlea, which is a spiral-like structure that is filled with fluid. The vibrations of the cochlea is picked up by hair-like cells attached to it. These hair cells act as receptors that generate electrical impulses. These impulses are sent by auditory nerves to the brain for interpretation. We have come to the end of the chapter. If you have any doubts, please approach Mr. Peck. Thank you for listening and have a nice day.